Hello, this is Jack Jackson. In this video we will be introducing the concept of a line integral, specifically a line integral of a scalar function of two variables. So this is a new type of integral, but before we talk about a new type of integral, let's review a little bit of an old type of integral. So in Calculus 1 we talked about a definite integral of a function of a single real variable. So let's review a few basic concepts from that. A definite integral of a function of a single real variable can be interpreted as a net signed area under a curve from the interval or line segment on the x-axis to the curve. So if the curve is above the x-axis, we're just talking about an area. But areas of between the curve and the x-axis that are above the x-axis add to the integral, and areas that were below the x-axis actually subtract from the integral. That's why I say a net signed area. But if we start with just a function that's all above the x-axis, like the portion of this function that we have here, then we're just talking about an integral. It's just talking about an area. So we define the integral from a to b of f of x dx to be a limit of Riemann sums. We take an interval, in this case it's a line segment going from -4 to 3 on the x-axis. That's indicated by these limits here. Here it is over here, -4 to 3. And so that's our domain, is a line segment. Okay? And above that line segment we have an area. The area we're looking for is actually this gray area on this picture on the right. But we approximate that by breaking the line segment up into some sub-line segments, sub-intervals, and finding rectangles above them. Okay, so the width of these intervals is delta x sub k. So you got a delta x for the first one, the delta x for the second one, the third one, and so forth. One way we could do this, although we do not have to do it this way, is to let delta x be b minus a over n, and where n is the number of the rectangles, and that makes them all have the same width. Often we did that for convenience, but it wasn't absolutely necessary. Then what we do is for each one of these, say we take the kth one, let's say maybe this one here, we have this kth sub interval, sub line segment, and we take anywhere on that line segment and pick an x. It can be at the right end every time, the left end every time, the midpoint, some arbitrary point in there, it doesn't matter. We call that x sub k, and then what we do is we take that x sub k, in this case it was at the right end, and go all the way up until we get to the function value, and that gives us a height of the rectangle. So this delta x sub k is the width of the kth rectangle. The x sub k is some arbitrary or systematic, whichever way, x in that interval. F of x sub k is the y value of the curve at that x value. So f of x sub k is a height, or could be negatives, could be a sign, could be a negative of a height. So a signed height times a width gives us a signed area. That's for one rectangle. Add those up for all of those. We're adding up the areas of those rectangles. That becomes a Riemann sum. If we want specifically a right Riemann sum, we can force xk to be a plus k delta x, and that always goes to the right side of the interval, like you see represented here. Then we take the limit as the number of subdivisions, in other words, the number of rectangles here, goes to infinity, and at the same time we need those widths to go to 0. If you choose things like we have down here, the widths will automatically go to 0 as n goes to infinity, and that gives us a definite integral. Okay, so we can look, we'll get to that in a minute. We can look at it here. Here's our formula, natural log of parentheses x plus 5 plus 4. And here we could start, these are right Riemann sums, and you can see me going through there, getting more and more rectangles. And you can see that limit process sort of in play as this becomes more and more and more rectangles. Notice that those estimates are changing, but they're starting to settle down. There's 200 rectangles. It's pretty much and almost impossible at this point to tell it different from the actual area, which is the definite integral. So in the end, that limit gives us the actual definite integral, which is this area. Okay, and so in this particular case, we're integrating from -4 to 3, natural log of x plus 5, and plus 4. Do the integral of that. Using techniques that we learned in Calculus 1 and more advanced techniques that we learned in Calculus 2, we can find antiderivatives for these different functions. And this one is a Cal 1 example. Evaluate that antiderivative at the top number minus and evaluate that one at the bottom number, and subtract those two things. That gives us the exact value of that definite integral, and that's using the fundamental theorem of calculus. And then we can put that in a calculator and get an approximation here. I'll let you work out the details of that antiderivative on your own and verify that this is correct. Now, if you just want the decimal approximation, then what we're looking at is you can do it the way we just did here, but you can also do it with some approximation technique, say using Simpson's rule or the numerical capabilities of your calculator or computer, and which is probably Simpson's rule or a variation thereof. Okay, so that's a quick review of Calculus 1 integration. All right, now let's take exactly the same thing, and I want to give it a slightly different perspective. Instead of graphing this in the xy plane, where the function y is the logarithm of x plus 5, then plus 4, let's let it be z equals log of x plus 5, and then plus 4. So now it looks exactly the same thing, but now this is the xz plane. And let's think of that now if we pull that back and look at it in 3D. So now we're looking at this region right here is an area in the xz plane, and the top is bounded by this curve. But this curve could be part of some larger surface, which is a function of x, y, and z. Okay, and that's the perspective we want to take. Okay, does everybody see what's going on there? And by taking this perspective, I want to generalize this idea just a little bit. So basically what we're doing is we're finding the area of one side of a wall or fence or curtain. Okay, and this one is a straight wall, or a straight fence, where the bottom of the fence is just a line segment along the x-axis here. Okay, but the height of the wall or height of the fence, okay, is variable. In this case, it's kind of tallest at this end and shortest at this end. And the height of that is given by values on this surface over here. Now, whatever formula makes up this surface, we're taking y equals 0 and plugging in that formula, and that is the intersection of this surface with this plane, xz plane, and that will be this curve. Actually, you can see it right here. It's one of the ones that got graphed. This one right here, this curve, which forms the top of our region. Okay, and so that's what we're looking at. Now, how are we going to generalize this? What we're going to generalize now is we don't necessarily have to have our fence be in a straight line or a wall. We could allow the bottom of it, instead of being just a line segment, to be some kind of curve, some kind of shape that is curvy. So this thing could wander around the xy plane a little bit and not necessarily have to stay on the x-axis. Okay, now our fence or wall is kind of got a curve to it. So let's look at an example there. So what if, look over here at the left first, what if we let the curve now be, well, here's part of a sine wave, Here we're letting x go from -4 to 3, and you're letting y be the cosine of whatever x is. So it's part of a regular old cosine wave. And so now we have a wavy bottom to our fence. We're going to have our formula. Well, it's almost the same as what we had. Our formula for the surface is z equals log of x plus 5 plus 4, which is what we had before. And then I'm going to say plus y as well. Well, before we had y as 0, so that last term basically just dropped off. But now, if we're at different places, the y's are not the same. This here is the xy plane right here. And so y's are not always 0, so that term will come into play and determine the heights. Now when we see that, then our curve, this curve here in the xy plane is the bottom of our wall here, which is a curve. Okay, here it is again from a different perspective. Okay, so this part here, that point is that one there. Okay, this one's kind of turned around. So this point out here is this point here on the y-axis is this guy up here. This guy here is actually, get my bearings here. This is positive, this is positive. So actually, that's the third quadrant down there. So that's this guy right here. This is the fourth quadrant here, is actually this one out here. So it's kind of rotated from what we see here. This one's oriented a little bit more the direction we're looking here. So these are all the same. This is exactly the same shape. It's just looked at from a couple of different views. I'll pull it up where we can rotate it around and look at some different views here. But in the end, then the height above this is determined by this surface here, and we end up with a nice little wall that looks like this, with it's a variable height, but it's got a curvy base to it. So I think I have, yeah, this is it here. So this is the curve here. So if you look at it straight from above, let's see, get it oriented their way. Turn it around. Well, we're almost straight from above. You can see the base curve there is what we have here, but the heights are variable. All right, it's going up and down. There you can kind of see a little bit what that looks like from a variety of different viewpoints. That's a pretty good view there. So you can kind of see what it looks like. Now, the height is given by values on this surface, and there's a portion of the surface right there. You notice that the top of the wall is cut off when it hits that surface. So the curve along the top is a curve that's above the domain curve, which is this cosine wave, but it's on the surface. Okay, so let me stop that. All right, so one way we can see this is to parameterize things. So if we parameterize this, just let x be t, then of course x is t, and y is just cosine of t, and we could get that surface also in terms of t. Now, how will we go about approximating this? Let's go back. So I could start by, I'll go back to here. We could start by approximating with a rectangle. And that's with the line segment going from here to here. But we'll probably want more than that. Let's put about 3 rectangles to get us started. So what we're going to do here is we're going to have we're going to approximate that area with areas of rectangles. And so the bases are going to be line segments. So what do I use for the base? Because this thing is curvy over here. I'm going to let the base be a line segment. It's a secant line segment going from one end to the other of our sub-curve. So here we've taken the curve and broken it into 3 sub-pieces. It's the curve going along like this, from this point to this point, the curve part, and then from here to here, and here to here. Now the way I've got it divided up right at the moment, I've got equal delta x's, okay, but not necessarily equal delta y's or equal arc lengths or equal t values even. I could divide this up different ways. These do not have to be the same, but we have different values here. Okay, and then so that's going to be really, it's the change across this way is the length. I'm going to call that length s, delta. It's the delta s. Okay, and we have a relationship between delta s and delta t. Let me go back to here and look at the picture here. Here I've got it broken up into 5 pieces. And here this is delta x, is the horizontal change. Delta y is the vertical change. Delta s is this distance across here, which is the length of our base. Now we have a different delta s potentially for each one of these things. So here's a delta s1. The length of that secant line segment is delta s2. The length of that secant line segment is delta s3, and so forth. So the width of the kth rectangle will be delta s sub k, which is also the square root of delta x sub k squared plus delta y sub k squared. So we have a Pythagorean relationship based on that right triangle for the Pythagorean theorem. So then what do we do for the height of the rectangle? We take some x value not on this secant line segment, but on the curve itself. It could be right at the right end, like a right Riemann sum, or a left end, like a left Riemann sum. But it could be some sort of midpoint thing, or really any point along here for an x1, any point along here for an x2, x3 is any x along here, and so forth. They could be any of those x's, and then we find the y value. I said x, it's really x and y, right? Because these are not along just the x-axis. The x's and y's are changing. So you have a point 1 here, which is x1, y1, a point in here somewhere that's x2, y2, and you take f of that to be the height of that kth rectangle. Multiply those two things. Now you have the area of the kth rectangle. So here you can see the 5 rectangles corresponding to these 5 pieces here. Sum those up, you're adding the areas of those rectangles. Take the limit of that as n approaches infinity and the widths of all those rectangles goes to 0, and we have what we call the line integral. It's assigned net area between the curve and the surface. Okay, and it's written this way. Sometimes you'll see it written with an integral sign with this little circle to indicate it's a line integral. Oftentimes that's not written down, so be familiar with either version there. So here, if you're noticing, I'm not sure what point they're picking here, but notice it's definitely not not the endpoints here. It's not always the right endpoint or left endpoint, because what would happen then is the corner would be on the surface, and that's not happening here. You can see, for example, this one here is sticking out on the bottom there over here and sticking out the top over here, but there's some place where this height is on the curve, and height here, and that if you go straight down from that point where that line hits, that x, that's the point somewhere about there that they're picking for the xy for that particular one, and coming up and finding the height. Like this one, it looks like it's hitting right there. If I could go straight down from that point, then right down here is going to be the point on the curve that they're using. Okay, but of course you see this you can obviously see this thing sticking out both above and below. This could potentially be an over or underestimate, by maybe off by quite a bit. But if we increase the number of rectangles, we're getting closer and closer and closer. So they're dividing it up. These little secant line segments are getting closer and closer to matching the curve, and these rectangles here are getting closer and closer to matching the area that we're looking for. Let's jump out like to like. Yeah, let's put a lot. 50. Okay, or even 100 if it'll do it. Let's see. Okay, and now we have a pretty good looking look at the surface. Okay. If we go back to 5, then here is the triangle I was talking about earlier. Delta x, delta y, delta s. So this delta s is the same thing we use to find our ds, which is our arc length parameter that we've talked about earlier. Now, here's another example here. This is a completely different function here, but again showing you the delta x here and the delta y for a particular one. Here we've got a curve in the two-dimensional xy plane. We have z values above this given by this colorful contour graph, which is really just the contours given in terms of color. So if we had the scale, which is missing here, we would have heights given by the values of z, which would be given by the whatever color that we have here. If we had some scale, this would work out. But the thing I want to point out to you is the xy coordinate is somewhere on this, but it could be all the way at one end, all the way at the other end, or somewhere, anywhere, actually in the middle here, which I can control with this slider. And so no matter where we are in here, take that. So whatever color, like say, we get on, say, the boundary between the, whatever, let's say on that green color, whatever height that green represents, that's going to be our z value. And of course we do this for every single one. So no matter how we divide this up, we don't have to do it in any kind of even way, but these delta s's are likely to be different. That's okay. And we don't have to really do any particular systematic way. We could pick this point anywhere in the middle. As long as we're going to take the limit in the end, it all works out to be the same thing. Okay, let's go back to our original function here. So one of the best ways to actually accomplish the goal of actually figuring out what this integral is to parameterize everything. Get everything in terms of, say, a parameter t. So if we can give parametric equations for that curve, then we can turn the integral into a definite integral of one variable, which is basically a cal1 integral. So we're going to turn a line integral into a just regular definite integral. So it's a typical strategy we use in math a lot, right? Take a problem and turn it into a problem you already know how to work. So in this particular parameterization, we know, we already saw this, that we let x be t, then y is cosine of t, and let t run from -4 to 3. That will give us the curve in the xy plane that we need. Now notice that x prime of t is just 1. Y prime of t is the opposite of sine of t. We're going to need that in a minute. Now our function that was our surface was f of xy is the natural logarithm of x plus 5 in parentheses plus 4 plus y. Now we can write that as a function of t by changing everything to t's. So x is just t, so this is natural logarithm of t plus 5, and we got plus 4. Y is the cosine of t, so I can substitute that in. So there's our function f. Now we need our arc length differential ds. The way to get that is to take x prime of t square plus y prime of t square and then square root that. Multiply that by dt. So in other words, dx over dt and then square it plus dy over dt, square it, square root of all that, and then you've got that times dt. So we already have x prime and y prime, so we just simply square those. 1 squared is 1. Negative sine of t squared is just sine squared of t. And then we got our square root, our plus, our dt. And so that all of that is ds. So when we're talking about the line integral over this curve of this function ds, okay, it actually turns out to be the definite integral for t dt, where t runs from -3 to 4. This is my f of t, right here, my original function, f, that we're integrating. That defines the surface for the top of the fence to give us our heights. This over here, all of this is ds. So ds is replaced by the square root of 1 plus sine squared of t dt. F of xy is replaced by natural log of t plus 5 plus 4 plus cosine of t. So everything's in terms of t. Now we're just back to a Cal 1 integral. Now, as is typically the case, when we have this arc length parameter, these integrals often become very nasty in terms of trying to find an appropriate antiderivative. It's sometimes either impossible or at least very difficult. Sometimes you can make them where they're not too bad to do by hand, but most of the time they're kind of not real nice. We often resort to some approximation technique. Here I ran this through a TI Inspire CAS, and it would tell me an exact answer if it knew how to do it, and it doesn't. It came back only with a decimal approximation. But at least we get a decimal approximation. So this area that we found of this wall here is about 44.8 units. Now, if you'll notice something, if we let the wall be of height 1 all the way across, that is, we just replace this function f of xy with the function 1, then this integral would become the area of that fence. But if it's a height 1, that area of the fence is the length of the base times the height. Since the height is 1, that integral becomes just the length. So arc length is just the integral of that ds. It's a line integral as well. And so we just a line integral of the function 1 ds. And this is exactly how we did arc length when we did these sort of things before. So again, our ds is the square root of 1 plus sine squared of t dt. We're just integrating that from -3 to 4. Again, the calculator did not return an exact value, but it gave me a nice decimal approximation there to many digits. So that area of that little fence there of uniform height is about 8.44, which is equivalent to that arc length. So one application of a line integral is to find an arc length. Another one is to find this area, and there are other examples as well. So this was line integrals of a scalar function of 2 variables, and we're going to extend this to look at a line integral of a scalar function of 3 variables in the next video.